Some more word problems. Example 2. Now we're going to determine the exponential function with an initial value of 12, increasing at a rate of 8% per year. And this isn't necessarily population, but it still fits that model that we had up above. P of t equals P naught. But this time P doesn't, we're not saying P has to be population. It works for population.
Works really well for population.
So here is our general formula. And so we have two things they gave us. They gave us the P naught and they gave us the R.
P naught always initial value,
yeah.
or P sub 0 or P 0 or whatever.
Yeah.
Hoity-toity people like P naught because it sounds cool.
Yeah. So when we plug in R, make sure you change that to a decimal.
Yeah, can't use 8. 8 here will totally mess up the whole problem.
It's 0.08, and so then to finish that off, you just want to actually add those together. Do you need your calculator for that?
Don't we have a T? Did we not have a T in there? Oh, we're just determining the function.
Just adding 1 and
0.08. I was ready to put like 40 in for T or something like that and
that's
find
all
out
it
how
asks
much.
us for. If that's what it wants you to do, that's what it wants you to
Bingo, bango, chitty chitty.
Okay, example 3. We're talking about bacterial growth, which is modeled by an exponential function.
Yeah, hey, by the way, this might show up in chem class maybe?
It might. You never know. Or in Viro or something like that.
Something sciencey.
Something sciencey.
Yeah, here you go, real life.
Suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000.
I don't know if I can do that. That sounds real hard.
Okay, so we can start off with this general formula we have, or you could even maybe go back to using A times B to the Z.
Oh, that's a good one too, yes.
So that would be just it's saying the same thing, but a slightly simpler way of looking at it. And one thing you might ask is, how do I know which of these I have to use? Because there are some situations where you have to use it.
Right.
In this case, they're not telling us a percentage.
Right. No, they're not giving us one.
We don't need to use this one.
Right.
If they gave us a percentage,
that would be the one to use.
Right.
Yeah.
What they do tell us is that we're starting with 100 bacteria.
That's the initial value part,
right,
which is what goes right in front.
Right. They tell us that this doubles every hour. Well, how much do we have once it doubles? If we start
twice
with 100,
as many.
So that's 200.
Yes.
So what we're going to do to figure out basically the rest of the stuff that is in here, we want B.
Right.
We're going to have basically another point that after 1 hour we have 200. Okay, because we're doubling.
Right.
Right? So they tell us it doubles every hour. So after 1 hour, this should be 200.
Okay.
So plug this in and solve for B.
Okay. I can do that.
Okay. So 200.
And I can do B to the first power too, because
Good.
It's just B.
Okay.
Mm-hmm. Where'd that 2 come from though?
Oh, I divided the 100 over.
Okay.
Oh, yeah, that's a good call. So I divided 100 over and got 2. B to the first is just B.
Because how many B's are there?
2.
Yeah.
There's 2.
To be or not to be, that is the question.
Sometimes it is. Sometimes it is. So B is 2, A is 100. It's to the x power. And what should happen is if it's giving us doubling time every 1 hour, that should always end up being 2. The times where we have to actually do more work is what if it's every 2 hours?
Or every 30 minutes.
Or yeah. If it's something other than telling you every unit, you have to actually do more work to figure out what's going on.
But if it's an even hour or an even number of days or weeks or years or whatever, then this is more simple.
Yes.
Yeah.
Okay.
Do we have to solve it?
Oh, yeah, we have to solve it. Just kidding, guys. We have to solve this.
You were going in the video mode.
Predict when the number of bacteria will be 350,000. So that's whenever. Go ahead.
What are you doing?
I'm setting it up. This needs to be equal.
Okay. I like to graph these personally.
Yeah, well, we might as well. That's the only thing we know how to do right now.
I mean, that's the easiest way to do it, in my humble opinion.
Okay.
And just move 350,000 over to the right-hand side and find where this graph crosses the x-axis.
Okay, well, let's do it.
All right. I'm going to look at my messed up differential equation here in the process. I don't want to talk about it, so don't ask.
I wasn't planning to.
Okay, good.
Well...
what do you? I can't see the problem anymore. Where did it go?
It's right there. If only the screen would cooperate, I could do it on the screen.
You know, for some reason, it likes to hide sketchbook when you put other stuff out there, and I'm not sure why.
100 times 2 to the x minus 350,000. We want to know where it goes through the x-axis.
Right there. Can you see right there? That's where it goes.
Is that not the y? Oh.
I got a really weird window. Okay, hold on. So 2 guys walked into a bar. The third guy ducked. No?
Why is a seagull called a seagull?
Because they see gulls.
No, because if they flew over the bay, they'd be called a bagel.
A bagel. You're funny.
Thanks.
Yeah, I'm almost there. Here,
I think it's going to take some window adjustment. It may take a while for it to get to 350,000.
It's going to take 11.773 hours.
Oh, well, that's not that much longer. So we would need to change our window if this would work, but it's not. We'd need to make our X max be bigger. We'd see that it would go through at, what'd you say?
11.773. That's where it crosses the old x-axis-rooney.
So at 11.773 hours?
Yes, because that's what we're talking about.
Or you might say about 12?
You could say about 12. Depends on how...
And it depends on how specific maybe
the
the
question
problem wants you to be. This would be a fine one to put the decimal.
I don't have a problem with that one.
Okay.